Green hydrogen promises a zero-emission alternative to fossil fuels, yet widespread industrial adoption is stalled by a prohibitive production cost. This economic hurdle is not a standard supply chain failure or a temporary market inefficiency that will resolve through simple scaling. The stubborn price of green hydrogen is dictated by a microscopic electrochemical reality. This model identifies the physical floor. Splitting water into hydrogen and oxygen requires a minimum input of 1.229 volts. Operating at this theoretical minimum provides perfect energy efficiency. The trade-off is that at 1.229 volts, actual hydrogen production drops to zero. A facility with 100% efficiency is commercially useless if it produces nothing. In this context, perfect theory represents an economic illusion. To reach commercially viable production speeds, we pay a significant energy penalty to overcome the molecule's resistance to splitting, a barrier represented here as the activation hill. Forcing the reaction at pace requires a kinetic push, applying raw electrical force to drive molecules over that barrier. Because of this requirement, commercial electrolyzers run at nearly 2 volts, nearly double the theoretical minimum, simply to maintain industrial flow rates. To produce green hydrogen fast enough to be useful, engineers are forced to actively sacrifice the system's overall energy efficiency. This table identifies where the energy tax is most severe, showing that losses are heavily concentrated at the anode during the oxygen evolution reaction. The anode faces a complex bottleneck. Stripping water molecules to form oxygen gas requires 4 separate electron transfers and intense bond rearrangements. Only ultra-rare metals like iridium oxide can survive the corrosive, high-voltage environment required to maintain this process at scale. Scaling up production creates physical resistance. As high industrial currents accelerate the reaction, oxygen bubbles multiply rapidly across the metallic mesh. These dense bubbles fuse into a gas blanket. This physical wall chokes the reaction by blocking fresh water from reaching the catalyst. High production speeds physically hinder the reaction, creating a state of molecular starvation that limits the system's total output. This diagram compares the polymer electrolyte membranes that divide the system. To reduce electrical resistance, the industry utilizes thinner membranes. Operators also pressurize the system internally, attempting to remove the need for expensive external mechanical compressors. However, the high internal pressure combined with extremely thin materials physically forces rogue hydrogen molecules backward through the polymer mesh. This graphic illustrates gas crossover. Hydrogen molecules breach the central safety barrier, polluting the pure oxygen stream with volatile fuel. As the pressure gauge moves toward the red zone, the internal environment nears the four. Not eliminate these physical taxes. The upstream renewable electricity powering the process must be exceptionally abundant and inexpensive just to reach parity. Defeating these bottlenecks requires nanoscale engineering, improving the precision of the hardware at the atomic level. This next-generation PEM electrolyzer stack is designed as reinforced armor against physical backlash. PTFE reinforced membranes reduce electrical resistance and prevent crossover leaks. Oxide alloy catalysts dilute iridium with ruthenium and tantalum, maintaining durability while slashing rare metal requirements. This massive industrial effort is a brutal struggle against molecular bonds, polymer resistance, and the rigid limits of physical science. Realizing the potential of green hydrogen depends on achieving nanoscale control over atomic interactions, moving beyond the simple deployment of solar infrastructure.